Sasha is a nickname for Alexander, where I come from. This is place where they speak like this. I'm going to give you an overview of extreme events. I'll try to make it as user-friendly as possible. I thank all the co-authors for contributing results. A very key notion in defining anything is figuring out what the heck it is. So what are extreme events? Everything being relative, extremes are certainly relative to something. And what I'm showing here are probability distributions that show where specific occurrences or specific observations fall and with what probability. So so basically extreme events are very large or very small or very rare in some way events relative to the rest of the distribution. So relative to normal events, they're very rare. And these, is there a pointer here? These basically fall in the tails of the probability distribution. So what we see here, is there a pointer, by the way? All right. That's okay. What is the most key notion, and probably will be key to understand a lot of the talks you will hear today, is the notion of frequency and intensity and their relationship. So what's shown on the x-axis here is, thank you, is intensity. Let's just assume this is the intensity of the temperature distribution. So these are actual temperatures from cold to hot. This is where most of the temperatures fall. This curve is high here because it has the largest probability of occurrence. So probability of occurrence is just basically the frequency with which specific events occur. So these are our average temperatures, let's say. Okay, this is the bell curve, or so-called normal distribution, and it represents temperature pretty well. Different variables, wind, precipitation, are represented by distributions that have different shapes than this. But I'm just using this as an example. And basically, what we see here are probabilities of events falling into this distribution, okay, occurring here. So let's say this is the distribution of temperatures in the current climate. Let's say summertime temperatures, okay, daily temperatures. These here are, this is a threshold above which about 5% of the distribution lies. We call that the 95th percentile because 95% lies below it. If a very simple climate change occurs, a warming that represents a shift in the distribution without a change in its shape, then you can see that the probabilities of events falling above this threshold are much larger. So basically, just a simple shift in the distribution, a mean climate change, you could say, causes a change in the probabilities of extremes. Okay, it increases the probabilities of hot extremes and decreases the probabilities of cold extremes. Also increases or makes the probabilities of heretofore unobserved extremes possible. Okay, there are different types of climate changes possible. You could have, for example, without a change in mean climate, you could have a change in the shape of the distribution, which changes the frequencies or the probabilities of extreme events. Or you could have a change that represents both a shift and a change in the shape. So that would, this kind of change would increase the probabilities of hot extremes, and it would actually increase the intensity of hot extremes as well, and it would decrease the probabilities of cold extremes without really changing much the intensity of cold extremes. Okay, so this really represents, I mean, the difference between weather prediction and climate. In essence, the individual events, the occurrences, the daily temperatures, we cannot predict. We cannot tell you what the temperature will be on December 13th, 2073, for example. But we can predict the shape of the distribution. So we can say with pretty good confidence in certain cases what are the probabilities, what is the probability density function from which the temperature on December 13th, 2073 will be drawn. Okay, so this is climate, and individual events that go into that with those probabilities are weather. This is, by the way, similar to quantum physics. There are no exact predictions of occurrences of specific events in quantum physics. All you can predict is the probability distribution from which those events are drawn. So now I'm going to make a big faux pas and give you an example, because looking at these plots, I think that the probability is highly unlikely that you came here bargaining for a statistics lesson this early in the morning. So I'm going to give you an example from actual climate prediction, but the faux pas is that I'm starting with the most preliminary results first. So what I'm showing here are projections of summertime daily temperatures for different subregions of California, Central Valley, Southern deserts here. You can see the colors represent the time. So basically, these are sort of our historical events in blue, and as time goes forward through yellow and red, it ends up at the end of the century. Okay, this is based on downscale projections from one climate model. And you can see, for example, that in this case, the shift that's projected is more or less a mean shift, something similar to this, although it's not exactly, because the extremes here become a little bit more probable, so you get more intense extremes and more frequent, very high extremes. But the rest of the distribution looks pretty similar. Although I must say that the low end, the intensity of cold extremes doesn't change as much as the frequency of them does. But so you can still have really cold extremes; they're just less frequent. Okay, in the southern deserts, the shape of the distribution actually changes. It becomes narrower. You can see the peak is higher. And the cold side is drawn in more than the warm side expands. So that means that there's going to be less probability of very cold events in the deserts compared to hot ones. And when we go to different regions, the south coast, for example, we can see there's a different signal here. The north coast is very similar to that. So coastal regions are actually projected by this model to both change in to shift and change shape, so that the large extremes, the heat waves, become not only more extreme but a lot more frequent compared to the changes we see at the other end of the distribution. So that particular shift looks more like this. This is a different way of looking at it, and what this is basically the difference between that 95th percentile, which is a threshold we typically use to define extremes, and the median, or the central tendency of distribution. So how intense are the heat waves in this case? Okay, and what I'm showing here is for different epochs, different projected periods, what is the difference between that distance, that heat wave intensity between these projected periods and the current climate. And what we see is that the heat waves are becoming much more intense, even compared to the warmer distribution of the future climate. So, and this is along the coast. And to me, what we're trying to understand, or beginning to try to understand, is how is the marine layer involved in producing this kind of change. Okay, here's a result that's a lot less preliminary. The red bars here show the historical observed heat waves. These are the daily events. Okay, very hot during the day, typical California events. Very hot during the day, and cooling at night. Okay, we see that the frequency of them has not changed in this observed period, and neither has the intensity. On the other hand, here these blue events are the ones that are hot at night. They're still hot during the day, but they're also hot at night. These are sort of the unusual events, and they're all bunched up at the end of the record. Their frequency and intensity is increasing. These are the individual events. This is the heat wave activity, so the summertime heat wave activity. This is the 2006 event, which had huge impacts on health. Specifically, you will hear about later. What we see is a big trend, specifically in these nighttime accentuated events. Well, what's the difference between nighttime and daytime events? The nighttime accentuated events are much more humid, and that makes for big impacts. Is this related to climate change? Well, here's a projection. So these are the observations I just showed you. Here's a projection, a simulation, historical simulation from a climate model. We can see that just as in the observations, the typical historical events are daytime dry events, and at the end of the record we have a couple of unprecedented humid nighttime events, just like in the observations. Are these just statistical flukes? Well, if we continue with the climate projection, we see that actually this climate model, which is very good at projecting various aspects of California climate, actually, and it has been verified for simulating heat waves for the right reasons in California, is showing that heat waves are in fact projected to change flavors. They're projected to become more humid and much hotter at night. You can actually, if you like to see these steeply increasing curves, you can go to this website and look at many different projections for specific regions of California and many different variables from different models. So what are the wintertime temperatures projected to do? Well, actually, regardless of the region, the wintertime temperatures are projected to shift more or less in this manner. So we have more intense and more frequent extreme warm days, and the intensity of the extreme cold days, interestingly, doesn't really change that much. Their frequency does. They're less and less frequent, but their intensity, see the red, actually extends to very cold temperatures in all of these regions. So this is another way of looking at it, but it shows the same thing. I'm not going to dwell on it. Here's a result on chill hours, a related variable important for agriculture. And what I would like to point out is that this particular model projection shows also this kind of shift, whereby, you know, under pretty advanced climate change, we still get very cold conditions every now and then. It's even possible to get unprecedented conditions. It's just that they're getting less and less likely. And you know, you could imagine in a few decades from now going through a period like this where, you know, the trend appears to have stopped. And people asking whether climate change is still real. But this is what we call in the business natural climate variability, or decadal variability, if you like. The trends are, the anthropogenic trend is on a longer time scale. Let me change gears quickly and talk about a few other extremes, just breeze through them. Precipitation extremes, well, there are a couple of major things that go on that basically work against each other in California. On the one hand, warmer air can hold more moisture, and so the intense storms should theoretically become more intense. They should produce more precipitation. There's more moisture in them. On the other hand, with climate change, the storm tracks are projected to move further poleward. So we're actually going to get less, we're projected to get slightly less frequent rainstorms in California, especially in the southern two-thirds of California. Because of this and other problems with modeling precipitation, we really don't know what will happen with precipitation extremes from most storms. There is an exception you will hear about in a second. Different results are very few, but inconclusive so far. Here are some observations from LAX. This shows the wettest precipitation in inches on the wettest day in the observations. We can see wettest day, wettest 2 days, several days out to a month. We can see that there hasn't been so far any change in precipitation extremes. Okay, as we go to longer periods, these results probably from representing local conditions represent more regional conditions. So you can see the huge El Nino of 97-98 produced the biggest extreme. In 1 month, more precipitation fell than is expected in a single year. Here is the time series for the observed south coast precipitation. And here we can see that although the magnitude of precipitation extremes hasn't changed on record, their frequency has become more frequent. Now, even if we don't know much about the extreme precipitation itself, we can say something about flooding because of temperature changes and because of the fact that most of the snow, most of the precipitation that falls in the state actually falls on the mountains in the form of snow currently. As climate warms, we expect storms to become warmer. As they're warmer, they will hold more moisture, but they can hold more moisture, but also the snow level will increase, and the warmer storms will dump more rain, which will run off, causing floods. Some of the biggest rainfall or precipitation extremes are caused by these so-called atmospheric rivers. You're going to hear about them more in one of the following talks, so I'm not going to dwell on it. But this is actually one of the things, one of the types of storms that are well simulated by climate models, and they are projected to increase in both frequency and intensity. These are warm events. What the climate models do well is orographic precipitation. These storms bring moisture at low levels, and when it hits the mountain, it dumps a lot of precipitation. So these storms are projected to have more moisture, and the more extreme, the extreme types of these storms are projected to increase in frequency as well. We already know that the ratio of snow to rain is falling, and for one thing, this results in less and less snow accumulation in the Sierra Nevada and other mountains. But by the same token, what doesn't fall as snow falls as rain, and it runs off, causing floods. There is a recent study that projects flooding in the Central Valley specifically to increase with climate change due basically to warmer storms, larger rain intensities, and even wetter winter soils. Okay, very briefly, the beginning of the 21st century has been marked by a drought, which has had a large southwestern footprint. And a recent study by Dan Cahan showed that basically that particular drought, which wasn't over quite at the time that the study was done, falls pretty much where you would expect the 100-year event to fall. Okay, and this is based on its duration and the soil moisture deficit. And what's projected by climate models is that in the future, the 100-year event will be a different type of drought that would be both longer and drier. And so this is a pretty high confidence result. And without going into the details of this, it's not so much due to changes in precipitation amounts as it's due to the warming, which results in declining snowpack, earlier melt, enhanced evapotranspiration, and drier soils. So this is the result for the Colorado River, where we get a lot of our water in Southern California. But in the southern part of California, we also expect quite a bit of drying occurring, whereas the northern watersheds may actually get wetter. This is probably the last extreme I'm going to show you briefly, the Santa Ana winds. These winds, and this is an important one to show because actually, whereas a lot of extremes that I've shown are actually increasing, this is one that's projected to decrease. And the reason for that is very simple. The Santa Ana winds are so-called katabatic winds, and they require a pool of very cold and dense air sitting in the Great Basin. That air, when it starts flowing down the hill, down the mountains, it accelerates on its way down. It's dense, basically, the Santa Ana winds require that cold and dense air over the Great Basin. Now, climate change is projected to warm the inland a lot more than the coastal regions, and so that pool of cold air over the Great Basin is expected to diminish, and because of that, the frequency and intensity of Santa Ana winds are projected to diminish as well, although they're also projected to become hotter and drier. Okay, this is something that I put in there in the talk, but I realized that the next talk is exactly on this subject, so we'll not talk about it, and just leave you with a few thoughts. First of all, the concept of frequency and intensity is really key to understand extreme events and their changes. Extreme impacts involve sometimes convergence of different extremes. For example, heat and humidity. It's very crucial to sustain a high-quality net of observations to understand how climate and especially extremes are changing, and also to help us gauge how well the models are doing. And models are our best tools to look forward, to project climate change. It's certainly very important to ascertain in each particular model that it recreates specific extremes for the right physical reasons. It's much more important in the case of extremes as it is in the case of mean climate. It's not always possible just to average a bunch of climate models together when you look at extremes. They have to be considered independently, and this requires a mechanistic understanding of phenomena. The last point is that a finer scale and better atmospheric and climate models are being developed, and they're really needed to go forward and understand the local details of how global climate change may play out in California and any region. So I'm just going to leave you with these to read about your favorite extreme, and thank you. I'm sorry to go over time.